Welcome viewers. Today we shall be discussing on the concept of test of hypothesis in this module 15. In any empirical exercise, the most important element that crops up after estimation is the testing of hypothesis for drawing any statistical inference. So whenever the model is being constructed and finally estimated, we need to know whether the sample observations are true representations of the population or not. So in this context, we can say that statistical inference is very important in any kind of data analysis. So for this purpose, we look for the testing of hypothesis. So by hypothesis, we mean a conjecture or a guess which is made or a claim is being done whether it is true or false. And depending on the claim, we set two types of hypothesis. So it goes by the null hypothesis, which is considered have no effect or no impact. So whenever we consider any kind of relationship between two variables x and y, and we want to claim that y is not affected by x, that is the null hypothesis we make. So by null hypothesis, we mean that it is a statement of the status quo of no difference or no effect. That means we want to say that there is no impact of x on y or any of the variables on y, and that is how the null is set. So in most of the cases, null is actually rejected or also accepted depending on the level of significance. Keeping in view of this, we move on to alternative hypothesis, which is just contradicting the null hypothesis. So whenever we are contradicting the null, we want to say that the effect or any kind of impact is expected or it can be explained. So in case of the alternative hypothesis, we can say that suppose consumption is affecting income, but in the null hypothesis, we always say that consumption is not affecting the level of income. So in this particular hypothesis, we say that null hypothesis refers to a population parameter, and in case of that, the sample statistic is being collected, and we want to claim whether the sample statistic is a true reflection of the population parameter or not. And that is how we can classify two types of hypothesis, which is null and alternative in the same regard. In order to define this type of hypothesis, we need to define a kind of a test procedure. So by test procedure, first of all, we check for the test statistic. So any characteristic of the sample is referred to as a statistic. So when we are dealing with a list of observations and we have the sample mean, so we say sample mean is the test statistic which is carried out from the level of the population. And then after the statistic is being defined, we want to explain on what basis the null hypothesis can be accepted or rejected. So for this purpose, we define two possible values of the test statistic. The first one is called the acceptance region, and the second one is called the critical region. The acceptance region means that it is within the 95% of confidence interval that the sample statistic is lying, and it is the true representation of the population parameter. But when we go for the critical region, we reject the null hypothesis and thereby we accept the alternative hypothesis. So acceptance region and critical region are very important in the regard of hypothesis testing. This goes back to the Z-test where we go for a normal population. So for a normal population, when we go for the Z-test, we want to explain the properties of this Z-test, whether the Z follows any kind of underlying normal distribution. And in this regard, we want to say that the mean of the normal population is being taken care of. So whenever we collect the data from a set of observations, we have the population mean, and based on the population mean, we take care of the population of these observations. Based on the population mean, we go for the sample statistic, and thereby we set two sets of hypotheses, null and alternative. And thereby we define the testing procedure for this normal population. And this Z distribution follows a normal distribution with zero mean and constant variance. And that is how the Z test for a normal population is being done. And that is how we can proceed for the testing of hypothesis when we consider the mean of a normal distribution and how can we apply in the context of classical linear regression model. go for the z-test for the mean of a normal population. Whenever we're defining the population to be normally distributed, we mean that it is a bell-shaped curve and it is symmetric. So as a matter of fact, we go for the z-test. This z-test follows the normal distribution, and so we can apply the parametric test. So in order to explain the test procedure, we want to go for the testing of hypothesis whether the population mean can be correctly specified by the sample mean. So this goes back to the concepts that are to be developed in order to build up the testing of hypothesis. So by the concept we mean that x1, x2 to xn is the sample observations. So whenever we calculate the x1, x2, xn, they are basically obtained from the sample, and we take it from a population which is normally distributed. This population has a mean of mu and standard deviation sigma. So when we talk about the population mean of mu and standard deviation sigma, these are the population parameters, and sometimes it may be known, it may be unknown. For example, we actually randomize that population mean is known, but we actually consider two cases, standard deviation which is sigma, which may be known or unknown. So basically we collect x1, x2 to xn from the population. These are the sample observations, and from there we go for the population mean and we go for the standard deviation in this manner. Next we have the population mean, which is mu, and then we want to specify the sample mean so that the sample mean becomes a true representation of the population mean. So in this particular regard, we go for x bar. So whenever we define x bar, we go for summation of xi. I is running from 1 to n divided by n, that is the total number of observations. And this gives us the sample mean. So actually in all this testing procedure, we have the claim that whether this sample mean is actually being correctly specified by the population mean. So in order to proceed for the test, we have to define a particular value of the population mean, because population mean can be of many values, but we assign a specific value, say that is mu0. So this mu0 is a specified value of the population mean, and we want to say whether the population mean is actually equal to this mu0. And so we want to test the hypothesis that whether the sample mean is equal to this specified value of the mu0, and thereby we set up the hypothesis testing. So whenever we are going for the hypothesis testing, we want to say that whether the sample mean is closer to the mu0 or not. And if it is closer to mu0, then definitely we can say that the null hypothesis would be accepted. And if it is away from the mu0, then we will say null hypothesis will be rejected. Because in the null hypothesis, we want to say that there is no difference between the sample mean and the population mean. So that means both values have to be equal, or the both values are different. This goes back to the test statistic that we define. By the test statistic, we mean a Z distribution, which is analogous to a T distribution, and it is also symmetric. So if we look at the Z distribution and look at the numerator, we have the sample mean x bar, which is obtained from the sample observations, minus mu0. This minus is actually giving us the significant difference between the sample mean and the population mean, which has a specified value. Because mu is equal to mu0 that we decide upon. So x bar minus mu0 must be equal to each other under the null hypothesis, but we claim that they are different from each other, divided by sigma x bar. This sigma x bar is none other than the population standard deviation, which is considered to be known or unknown. So when we look at sigma x bar, it is actually the standard deviation of the sample mean. So if we look at the next step, we observe x bar minus mu0 as it is in the numerator, but in the denominator we have sigma by root n. That is what we get, the sample observations x bar, and its standard deviation is sigma square by n. So since we are taking the standard deviation, it becomes sigma by root n. So as we go for this, then the root n comes up into the numerator, and as it comes up in the numerator, we have root n multiplied by x bar minus mu0 by sigma. This sigma is considered to be the population standard deviation. So we can see that the population standard deviation is basically unknown. So we go for the sample standard deviation because everything is based on the sample, and we replace sigma by small s. So here S stands for the sample standard deviation. So this basically goes back to this expression of the z, which says that it is actually equivalent to root over of n, which is the number of observations taken the square root, x bar minus mu 0, which is in the numerator, which says that the sample mean must be closer to the population mean, or which is having a specified value mu 0, divided by s, and s stands for the sample standard deviation because population standard deviation is unknown. So thereby we set up this test statistic. So this test statistic is called z test statistic, which is going by x bar minus mu 0 divided by sigma x bar. Now as we move on to the concept of acceptance and the critical region, we basically want to explain how this concept can be developed. So in order to develop it, we go by some of our basic analogies. First of all, we go for the acceptance and the critical region because these are the major components of setting up any testing of hypothesis. So we come for acceptance or critical region depends on two important paradigm. One is null hypothesis and the second one is alternative hypothesis. So H0 stands for null and HA stands for alternative, A for alternative. Now we know that this Z distribution is basically a symmetric distribution, so we go for two-tailed critical region. Two-tailed critical region says that in the null hypothesis, we always say that the population mean mu is equal to the specified value of the population mean, which is mu 0, because we claim that there is no difference between the population mean and the mu 0. But in the alternative hypothesis, we say that population mean is different from the specified value, so that we can invite two different cases, whether the population mean is greater than the value or it is less than the value that we assume. So based on this, we set up two decision rules. The first decision rule is this, which says accept H0 if. H0 means we are accepting the null hypothesis if we want to say that the computed value of the Z statistic is lying in between the two lower and the upper bounds. This lower bound is basically at 0.25 level of significance, because if we consider the 5% level of significance as our acceptance limit, then alpha is 5. So alpha by 2 comes at 0.25 level of significance, which is in the negative tail of the distribution. And in the positive tail of the distribution, we have alpha by 2, which is 0.25. So within minus 0.25 to plus 0.25, if the value of Z lies, then we will say that there is no difference between the population mean mu and mu 0. So we are accepting the null hypothesis. On the other hand, if we want to say that the null hypothesis is to be rejected, then we go for reject H0 if Z is less than minus of Z alpha by 2. That means if the value of the Z is lying on the extreme two tails of the distribution, either it is on the left tail, which says that the value is less than minus 0.25, or it is in the right tail, then we can say that the null hypothesis is rejected and the alternative is accepted. So this gives us the claim for two-tailed critical region. So in most of the test statistic, where the test statistic follows a symmetric distribution, we go for a two-tailed distribution in this way, where we claim for greater than and less than both the types. But some of the distributions are one-tailed critical regions. So when we go for one-tailed critical regions, we go for H0. In the same way, we consider mu less than equal to mu 0. In this case, we have to identify the difference. We cannot write mu is equal to mu 0 because we cannot invite two cases. Either we operate on the left tail of the distribution, or we operate on the right hand side of the distribution. So depending on that, we have to set our decision rules. So if we set our decision rules on H naught, where population mean is less than equal to the specified value, then automatically the alternative hypothesis will be opposite, that is mu is greater than. So whatever we claim in the null, we have to contradict in the alternative, and so the alternative comes up as mu greater than mu 0. So in this case also, we set up our null hypothesis on the graph that z less than equal to z alpha. Again, one point to be noted, here we refer to alpha because it's not a two-tailed distribution, it's not alpha by 2. So either we accept or reject our decisions at 5% level of significance. It's not at 0.25% level of significance. So we accept H naught if z is less than equal to z0, or we reject H naught if z is greater than, depending upon the inequality that we have imposed in H0 or HA. Similarly, if we operate on the right hand side of the distribution, we go for mu greater than equal to mu 0. So suppose mu 0 is 5 or 10 and we claim that the population mean is greater than equal to 10, then the alternative would be population mean is less than 10. As we can say, alternative always contradicts the null hypothesis. So given this, we also set our decision rules and we say accept H0 or accept H1, and in this way we can go for the inequalities that are there in the respective hypothesis. So for this testing of hypothesis, two type of tail distributions are being considered. One is considered to be the two-tail distribution and one is considered to be the one-tail distribution. And for all of these cases, we go for the Z statistic, which follows the underlying normal distribution. So for the critical region, acceptance and the rejection, we have to follow the Z distribution and we have to take our decisions. Either we operate at alpha by 2, where equality sign is there, or we operate at only alpha, where greater than or less than signs exist. Now we go for the case when the population mean and the population standard deviation are unknown. So whenever they are unknown, we have to estimate from the sample observations. So this goes like this, that let x1, x2 to xn are the sample observations from the population, where we have the population mean, which is mu, and the standard deviation sigma. Now these both mu and sigma are unknown. And now since they are unknown, we have to actually get the sample observations, and from there we have to get the sample variance. So in order to go for that, we follow the same procedure, like we calculate the sample mean, which is x bar summation of xi by n. And since sigma is unknown, we have to get the estimate from the sample, and that will be called the sample variance, or we go for the square root of the sample variance, that is sample standard deviation, which is represented by small s. So which goes like root over of summation of xi minus x bar whole square divided by n minus 1. Because this n minus 1 means one of the parameters is lost, so it has n minus 1 degrees of freedom. So here also we go for the same kind of hypothesis, where the population mean is actually equal to a specified value, which is mu 0. In order to do that, we go for the same kind of statistical distribution, which we refer as T distribution. Again, it's a symmetric distribution, and so we have the same component in the numerator, which is x bar minus mu 0. This x bar is obtained from the sample. Mu 0 is a specified value of the population mean. So we want to say whether the sample mean is truly represented by mu or mu 0, and under null hypothesis they are equal. So that means there is no difference, and in the alternative hypothesis they are different. In the denominator, we have a change because here we cannot write sigma by root n because sigma is unknown. We have actually estimated from the sample. So instead of sigma, we write S. So this distribution follows n minus 1 degrees of freedom because one of the variable is lost. So in this particular condition, also we go for two types of hypothesis testing. The first one we set for the alternative hypothesis, and accordingly we decide on the critical region. See, if the distribution is considered to be a two-tailed distribution, then just like mu not equal to mu 0 we consider, which we consider when the population variance is known as well as unknown, and we take the decision on the basis of t less than minus t alpha by 2 or t greater than t alpha by 2. So this alpha by 2 is 0.25 level of significance, and we operate on the left hand and the right hand tail of the distribution. Similarly, we go for alternative hypothesis if we operate on the left hand side or the right hand side. So in this particular condition, we can go for mu greater than mu 0. Then accordingly, we follow the inequality in the null hypothesis. We accept the alternative hypothesis if t greater than t alpha, or we go for t less than minus of t alpha. Here we can write a minus sign before t because this t is a symmetric distribution. So this is what we follow whenever we discuss in case of a testing of hypothesis given the population parameter is unknown or the population variance is unknown or standard deviation is unknown. So we can see that two critical levels have been considered. If the distribution follows a two-tailed distribution, we go by t alpha by 2. Alpha is 5%. So at alpha by 2 level of significance, we take up the decision, or otherwise we take at t alpha, which is in one tail or two tail of the distribution. So this basically refers to the critical values as we explain. This graph is a bell-shaped curve which is a symmetric distribution, and so alpha by 2 is either on the right hand side or on the left hand side. If it were on the left hand side, we would have written minus of alpha by 2, but this is alpha or alpha by 2 depending upon the two-tailed test or the one-tailed test. And the value of the t, wherever the arrow is projected, is referring to the t value of alpha by 2 or t alpha, and accordingly we take a decision whether we are in the acceptance region or we are in the critical region. So this basically gets into our discussions on the hypothesis testing under a simple linear regression model, because that is the CLRM where we apply these techniques or these tools. Now we go for the applications of this testing procedure in the context of simple linear regression model. So for a linear regression model, we apply the t-test, which is already being discussed as a symmetric distribution. So under the t-test, we go for a t-statistic where we want to claim that the slope coefficient, which is given by the beta 1 hat, which is basically estimated from the sample, whether it is significantly different from the population parameter of beta. And in the denominator, we have the standard error. So just as we define a z statistic, keeping in view the same analogy, we go for the t-test and we frame this kind of formula, which is actually stated as beta hat 1 minus beta divided by standard error of beta hat 1. Now, in order to go for a t distribution, and if we go for a symmetric distribution or a two-tailed test, then we want to say that the null hypothesis will be rejected if the computed value of this t0 is exceeding the table value. What do we mean by the table value? It means that t at 0.25 level of significance and when there are n minus 2 degrees of freedom, because two parameters alphas and betas are to be estimated, so degrees of freedom is n minus 2. Similarly, when we go for the t-test for equality, That means when we go for the t distribution and it is symmetric, we say that the population parameter is specifically equal to a particular value, and the alternative is that it is not equal to the value. So depending on that, we go for a t statistic, and here we assume that the sigma is unknown. So we cannot go for the sigma, and we have to estimate it from the sample. So from the sample, we get this formula as the standard error of beta hat 0, and thereby we go for the intercept coefficient. So the intercept coefficient testing is done in this formula, and here we go for the intercept testing for the alpha hat. So similarly for beta 0, which is the intercept term, and beta 1, which is the slope term, and for both the cases we can go for the same testing procedure. So this goes back to an empirical example where we go for the infant mortality rate is a function of, say, child immunization. So we go for the model has alpha 1 and beta 1, which are actually estimated as alpha 1 hat and beta 1 hat. And based on the result, we can see that the probability values are less than 0.05. So we mean that the null hypothesis is rejected, and we can claim that the child immunization has an impact on the infant mortality rate. And that is how we can explain that how the testing of hypothesis is being applied. So the standard error is 0.14, and the 1.07 is the value of the beta 1 hat. So if we divide 1.07 by 0.14, we will get the t value, and which is statistically significant. Similarly, if we divide 117.6 by 7.81, we will get the corresponding t statistic, which is also significant at 5% level. So finally, to sum up, in this particular module, we have arrived at the concept of the test of hypothesis, which means two types you have considered, alternative and null. Then we have discussed about the one-tailed test, where we go for the alpha, which is not divided by alpha by 2. For the two-tailed test, we can invite the equality cases so that both of them are invited, greater than and less than inequalities. And finally, we have interpreted the slope coefficient of a regression model, how this can be applied. And that is what the discussion with regard to this particular module.